Okay, ladies and gentlemen, put your heading on your paper. And today, my objective for you is to teach you the definition, the characteristics of inverse functions and relations. Let's talk about that word relations. See it up there in the heading? A relation is simply a graph, a set of points. So the graph could look like a line, it could be a parabola, it could just be a random group of points on the graph. So a relation is a set of points. Now, what makes a relation a function is if the relation passes the vertical line test. Do y'all remember that? If it passes the vertical line test, then the relation becomes a function. Today's definition, inverse relation. Two relations are inverse relations if and only if whenever one relation contains the element AB, the other relation contains the element BA. I like that definition. That's easy. So that means if this relation has the point 4, 7, this relation, if it's the inverse, must have the point 7, 4. That's a pretty easy definition. Okay, so let's say they're functions. Here's a property of inverse functions. Suppose f and the inverse of f, ladies and gentlemen, do me a favor. Let's stop right there. Will you circle this symbol f to the negative 1? And will you remind yourself that that's the symbol for inverse? That negative 1 power is the symbol for inverse. Okay, if f and the inverse of f are truly inverse functions, then f of a equals b if and only if the inverse of f of b equals a. So we're literally interchanging input and output. Okay, so, ladies and gentlemen, example. Find the inverse of the function f of x equals 2/5 x minus 1/5. Then graph, which I've already kind of helped you with the graph on this example. Okay, I've divided this up into 3 steps just to help you organize your work. The first step, let's replace our functional notation just with a regular y. Everybody is comfortable with the fact that f of x just equals y. So here we go. Y equals 2/5 x minus 1/5. Okay, if I need to inverse a function, you must switch. Another word we can use is interchange x and y. Okay, so I'm going to change colors here, and I'm going to rewrite this equation. X equals 2/5 y minus 1/5. Okay, now that's technically your inverse function. But to simplify this, let's solve for the new y. So step 3, solve for y. One thing I like to do, algebra students, if I have multiple fractions, I like to multiply through by the common denominator. I like to teach my students to do this. You make fewer mistakes if you have fewer fractions. So 5x equals 2y minus 1. Add 1 to both sides. Divide everything by 2 here at the end. So y equals 5/2 x plus 1/2. And To make it look official, at the end here, let's go back to functional notation. So let's use our inverse symbol, which is this -1 power. So ladies and gentlemen, in purple we have function f. In blue we have the inverse function of f. Inverse. Any questions on step 1, 2, and 3? Because that's what I'll have you do here at the bottom of the page. Any questions? Okay, now let me show you how these two functions relate to each other on the graph. Ladies and gentlemen, do you see where I have graphed for you f and the inverse of f? 2 lines. Here's the important relationship that I want you to see. Will you graph, let me see if I can see it well enough to draw the graph. Will you draw the line y equals x? That's our linear parent function, y equals x. Sketch that in, will you? Okay, you art students out there. Would you say that f and the inverse of f are reflections of each other across the line y equals x? If I were to fold this paper along the line y equals x, would all of the points match up? They're reflections of each other. Okay, here's an interesting fact. I don't care what inverses you graph. They can be inverse lines, they can be inverse parabolas, they can just be inverse points. Inverses will always be reflections of each other across the line y equals x. Will you take just a couple of minutes now and see if you can work number 1 and 2 at the bottom of the page, and then we'll move to the back.